And in this video we are going to discuss Leetcode problem, shortest subarray with sum at least k. This problem is marked as hard on Leetcode, and there is a slight variant of this which is marked as medium, and we'll discuss both of them in this video. So the problem is that we are given an array A with both positive and negative values, and we have to find a contiguous subarray of A such that the sum of elements of that subarray should be greater than or equal to k. And of all those subarrays, we have to return the length of the shortest subarray. So for example, if our given A matrix is this, then and k is equal to 3, then we have 3 subarrays such that sum is greater than or equal to k. So we have this subarray whose sum is 3, we have this subarray whose sum is 3, and we have this complete array whose sum is 4. So out of these subarrays, the one with the shortest length is this one, 2, 1, and hence answer is 2. So to solve this problem, we'll first create a cumulative sum matrix P. Let's say Pi stores sum of first I elements of A. Sum of first I elements of A. So the first element of P would be 0 because sum of first 0 elements of A would be 0. Then the next element would be 0 plus 2, that is 2. The next element would be 2 plus minus 1, which is 1. The next element would be 1 plus 2, which is 3. The next element would be 3 plus 1, which is 4. So basically P1 stores sum of first element, which is 2. P2 stores sum of first 2 elements, which is 1, and so on. So if j is greater than I, then Pj minus Pi would be the sum of first j elements of A minus sum of first I elements of A. So it's basically the sum of I plus 1th element of A up to jth element of A. So if once we create this cumulative matrix P, we can forget about A. We'll use this matrix P to solve this problem. So we have to find two indices y and x such that Py minus Px is greater than or equal to k. That is, it will correspond to the subarray of A such that the sum of subarray from x plus 1th element in A to y'th element in A would be greater than or equal to k. And since we have to minimize the length of this subarray, we have to find x and y such that they are very close to each other. So for every y, we want x to be largest possible. So the greater the x, it's better, and px to be smaller. The smaller the px, it would be better. So for example, let's consider this element 3. So I have here marked the indices of the array P, and we are focusing on the value 3. So we have to find all the x in array P so that Py minus Px is greater than or equal to k, and we can only find one such x, which is x is equal to 0. For the index 0, 3 minus 0 is greater than or equal to 3, but for rest of the indices, it's not possible. So if we go to index 1, then 3 minus 2 is not greater than 3. If we go to index 2, then 3 minus 1 is equal to 2, which is not greater than 3. But so there is one algorithm that for the current element, we compare it with all the previous elements, and if the sum is greater than or equal to 3, that is Py minus Px is greater than or equal to k, we update our answer accordingly and update it with the minimum possible length. The alternative is this, that for 3 we don't need to compare it with the index 1 here, because while going from 1 to 2 we are increasing the index as well as decreasing the value, which means that if 3 minus 2 is greater than equal to k, then 3 minus 1 would be greater than equal to k, and we are getting a better index, that is 2 is better than 1, which is closer to 3. So the idea is this: we'll maintain a queue so that the indices in queue will have an increasing order when we will consider the corresponding values of those indices in the array P. And for a given index y, where the value is py, we'll compare y with only these indices maintained in queue, and this is a doubly ended queue. Let's say this is front and back of the queue. We compare these values only with the indices. Compare this index only with the indices in this queue, because let's say there was an index x such that px is greater than p of in, and x is less than I, and x is somewhere here, let's say. Then there is no use to maintain that index, because if py minus px is greater than or equal to k, then py minus pn is also greater than or equal to k. Because pn is smaller than x. Pi is smaller than px. So why to compare with such an index x? There's no point. Hence we will only store indices in this queue such that they are in an increasing order to reduce our work. So what we'll do is that we'll first see that is py minus p of i1 greater than or equals to k. If yes, then we update our answer to be minimum of current answer or the length y minus i1, whatever is the minimum. And if this is true, we'll remove the index i1 from the queue, remove from front, because any index y dash greater than y which satisfies p of y dash minus p of i1 greater than or equals to k, the y dash minus i1 length would be greater than y minus i1 length. So we can't do better. So once we have got an index y such that py minus pi1 is greater than or equal to k, we can safely remove i1 from that queue. So we'll remove from front, and we'll keep on doing that until we reach an index a such that py minus pa is not greater than or equals to k. So our new queue will start from a, and then the next index to a, let's say I of k, and up to I of n, and we'll remove all these values which are less than a. Let's say a is here, we'll remove all these values and update our answer accordingly, because they are no longer needed. Similarly, so this is the first step. The second step is for the next index y plus 1, we still need that, we have to maintain that invariant that q should be in increasing order of p values. Q indices should be in increasing order of p values. Because of the argument we made earlier. So what we'll do, we'll also remove some elements from the back of the queue up to index, let's say b. If these values are greater than p of I, let's say all these values corresponding to these indices are greater than p of I, and all of these are less than p equals to p of I, then in fact less than p of I and greater than equals to p of I, we'll remove these indices and then we'll store the current index y into this, so that these values, the p values corresponding to these indices, are still in increasing order. And this would be helpful for our next index y plus 1, and we'll keep on doing that until we explore all the indices of array p. So I hope this algorithm was clear to you, and now let's consider a special case. A special case is when a is constrained to have only positive values, only positive elements. In that case, we don't need to maintain array p or maintain a queue. So we don't need either of them. Reason is that an array p will always be in increasing order. So the queue that we were maintaining would have all the indices 0, 1, 2, 3, 4, 5, 6. So basically, if this is the front and this is the back, and we are considering an index y, then py would definitely be greater than p of y minus 1. We will never remove from back. Never remove from back. And we have to remove from front if py minus whatever the value at front is, pf, is greater than or equal to k, then basically f is done and we can remove it. But we can achieve the same purpose by maintaining a pointer L, such that let's say our a is only positive values 2, 1, 3, 4, and k is let's say 5. So initially L is 0. So L will point to the lowest index from which we are measuring our sum. So initially our sum will be 2, L would be 0, and we'll explore the indices of A. So initially our sum is 2, not greater than k. Sum is 3, not greater than k. Sum is 6, greater than k, yes. So in that case, when sum is greater than k, we'll update our answer first. Now answer is basically 3, and we'll move L and try to see that if can we shrink this and get a better answer. So we'll move L here. L is equal to 1, and sum would be 6 minus 2, which is 4. We'll consider this sum, which is 4. Is greater than k? No. Then we'll move forward. We'll move here. We'll get a value of 8. So is 8 greater than k? Yes. But answer is already 3. We can't do better. Now we'll try to shrink this. Whenever we get a sum of greater than k or equal to k, we'll try to shrink this by increasing our L. So L is 2. So now from L to the current index I, the sum is 7. Is 7 greater than k? Yes. And is length better than the previous length? Yes. So answer becomes 2. then we'll increase our L equals to 3. So now the sum from L to I is simply 4. Is 4 greater than K? No. So we can't do better, and answer is 2. So what I mean is that we don't need this Q, because we can simply store the sum from index L to I and if sum is greater than equals to K, then we keep on moving L while sum is greater than equals to K. We keep on increasing L and updating our answer if we are getting a better answer than previous, and if not, we'll keep on updating sum, else update sum with new values, and hence using this algorithm we can get the minimum size. So what I'm trying to say is we don't need to remove from the back first of all, and removing from the front, removing an element from the sum front is equivalent to increasing our L pointer, as we are trying to shrink the size of the window of A to still get the sum greater than equals to K. So that these two steps are equivalent. So now let's try to see this algorithm in code. Look at the code quickly. So this is a case when our array A, which is array nums, contains all the positive elements. So in this case, let's store the size of the array in n. Let's initialize our answer to be infinity. So our sum is 0, our current index L is 0, and we iterate over the array nums. We add the current value to the sum, and while sum is greater than equal to s, which is basically k, sum is greater than equal to the required value, then I'll update my answer, and then I'll move the L pointer one step forward and see if sum is again greater than equals to s, and we'll keep on updating our answer and keep on shrinking the window size as discussed earlier. And finally, if the answer is not equals to infinity, that if we had done better, then we return the answer. Otherwise, we say that we have not found any subarray, and we simply return 0. So now let's move to a more generic case when negative values are allowed. So in this case, we have an array A, we have a value k. So we store the size of array in variable n. Then we create the cumulative sum vector p. We initialize a doubly ended queue. We initialize the answer to be int max. Then we iterate over the array p. So as discussed earlier, the first step is that if pi minus p of whatever the index at front is, if this value is greater than equals to k, then we update our answer and we remove that index from the front, because that index is no longer useful. We can't do better with that index. We keep on doing that until we reach an index such that this value does not hold, this condition does not hold. The second step is to remove from the back. So to maintain the property that the indices in our queue are always in increasing order, what we do is that if the value at the back index is greater than the current value pi, greater than or equal to the current value, we simply pop from the back. We insert I only when Q has all the indices such that value for those indices is less than pi. And after doing that, we just simply add the current index at the back. Finally, if answer is still infinity, that is we couldn't find any subarray with sum greater than equals to k, we return -1. Otherwise, we return whatever answer we have got. So I hope you like this video. Please feel free to share it with your friends, comment, subscribe, and stay tuned as I'm trying to create more and more good content. See you. Goodbye.